Hey guys, hope I am audible. Yeah. Okay, so I guess you can see my screen. We are going to look at a very interesting and important topic for all computer programming, and that is least common ancestor. And we will see how we can solve it efficiently. So there are many, multiple methods to solve it efficiently. We have multiple methods to solve this problem efficiently. And we will be looking at specifically one problem, which is binary lifting. Okay. This is one of such methods which help us solving it very efficiently. We are going to see it. Before that, let me know how good you are at graphs and trees. Have you solved problem on graphs and trees, all of you? Do you know what this LCA basically means and what are the naive methods of solving them? May not be binary lifting, but what are some basic methods of solving them? Are you aware of that? Or where do you see yourself? Are you a total beginner? Are you absolutely a beginner, or do you know these topics to some extent? Because in this topic there are many associated things which are quite interesting. So I would be adapting my pace as much as possible to the best, the best reach as per the audience, right? So maybe some feedback from your end would be good. I think it is. Uh, you can write down in the chat, and I should be able to see that. Should I go with an absolute beginner perspective or should I step with an intermediate kind of understanding? Hi Dilip. So I hope you can hear me, all of you. So the question is that where do you see yourself? Are you a beginner or yeah, hello Selvamani. What kind of an explanation are you looking forward to? From the beginner, I'll step into the thing slowly, gradually, and I'll okay, beginner, great, fine. So then let us make it, let us structure our content. Uh, Let us say we are going to cover certain things. Do you all know linked lists? Do you all have idea of linked lists of trees and of rooted trees? So trees and rooted trees and binary search. I hope to some extent you have used all these things because these are some basic things which are essential, right? You all have solved problems on these, right? You know what are linked lists, you know what are trees, what are rooted trees. Okay, great. So these are the only things which are required. And let us start with an interesting question now. You have used binary search, and when you do binary search, the code looks something like this, that you have some L and R which are initialized, and then you say that while L is going to be less than equal to R, difference between trees and rooted trees. Okay, so rooted trees means there is a particular root, and we have a very distinct parent-child relationship. Every tree will have a root, but again, suppose we look at this particular tree. So this is an undirected tree. We are talking about an undirected tree. So we can say like this can be A, B, C. So if A is the root, then it will look something like this, that B and C are the children of A. But we can again position the same tree as C that will come to B and that will come to A. Something like this. We can say something like this. The edges are the same. There are two edges. One between, I'm sorry, over here we will have A. So just a second. So over here we will have A, and over here we will have B. So we'll have B over here. Yeah. So now what we can say is we can have CAB and these two are same with respect to the edges they are having. There are two edges, but the thing is that the moment we say that it is rooted, these two are different. One is rooted at A, another is rooted at C. But in terms of an unrooted tree, they are the same thing. Okay. And when we talk of an ancestor, the fact is the parent-child relationship is very distinct. Over here, you can say that A is a child of C. But over here, if this is a rooted tree and A is the root of the tree, you cannot say that A is a child of C. Over here, A is a child of C, but over here, C is a child of A. So this is actually the difference between a normal tree and a rooted tree. Normal tree means a connected graph which will have no cycles, right? And what is a tree? Yeah, we mentioned what is a tree, a connected graph with no cycles. Any connected graph which will have no cycles is going to be a tree. If it is not connected, if we only ensure that it does not have any cycles, we will say that it is a forest. Basic terminologies, right? So anyway, this is what you need to keep in mind, that when we talk about ancestors, we only talk about rooted trees. Because in an unrooted tree, there is no distinct parent, there is no distinct ancestor as such. Okay. So that is the idea. You can make like, there will be a lot of ambiguity. That is why we say that there will be a single root. And from there we will descend. And one root can have again many children. We are not saying that it has to be a binary tree, but a rooted tree means that the parent-child relationships are very distinct. I'm sorry. Only the leaves are such nodes which will have no children. Okay. Cool. Now coming back to the question, we are talking about binary search. How does binary search work? It is something like this. We say that we are going to assign a mid, int mid equals to something L plus R by 2, and then we will use some conditions and we will change the values of L and R in that manner, right? Now, there is a certain assumption that we make, which is if A mid is less than some target or greater than some target or greater than equal to something we do, and we say that this particular operation is easily feasible. We say that at any point of time we can find out the middle value of A. We can find out a certain value at a certain index of A. This is an assumption which works because we are dealing with arrays. And arrays are such data structures which are indexed. Now the question is, can we perform binary search in a linked list? Suppose you have got a linked list. Can we perform binary search on a linked list? If yes, why? If no, why? If yes, how? If no, why? So we again have these elements we have for all of them, and I will ask you Q queries. Every query, so there will be n elements once again. Now I will ask you Q queries. Q can range up to 10 to the power 5, and the number of nodes are also as large as 10 to the power 5. I will ask you every time that the list is sorted. The list is sorted, and I want you to find the node which is going to help me. So I don't want to use so much of space. You cannot use any other data structure like hash set. You can only use a linked list, and you have to tell me for all these queries. Every query will ask me some target, and you have to tell me whether that value is present or not. Simple. It's linked, that's why we can't apply binary search. Okay, it's not indexed. Yeah, so all of you are coming not access mid every time. Not access mid, right? It cannot access mid, or in other words, if we have to access the mid position, we have to take multiple steps, right? So from here, if we say that we are always starting at the beginning, we are currently over here, we have to say in order to reach the mid position or certain position, we have to take the steps one by one. We cannot gallop. Makes sense? Now, you have got Q queries and you can do some pre-processing. You can do some pre-processing on this. And the idea is that can we use some kind of pre-processing to make this task possible in a feasible amount of time. Now for every query, if I take n steps, then I know that n is also going to 10 to the power 5. So the total number of steps, if we sum them up, it will get increased to 10 to the power 10, which is way larger than we can handle. So we can somewhere figure out that using some pre-processing, if we could you know, find out if you can apply binary search, it could have helped us, because for every query, if not n, if we apply log n, it could have helped us. So therein comes the second approach of binary search. So there is another approach of binary search, and this is how it goes. Suppose again you have got an array, and now you will apply something like this. You have some elements, we can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Suppose you are looking for 9. You can say that for the first time, when I am at the beginning, I know that L is equal to 1, R is equal to 10. I will not be adopting the idea of L plus R by 2. What I'll say is that I'll try the highest power of 2 in front of me. I'll try the highest power of 2. Suppose over here we know there are 10 elements. So let us say 2 to the power 5. I will try a hop of 2 to the power 5 from here, and I will check if the element where I reach, if that exists, is that less than equal to the target value, or is it greater? So look over here, when I add this 32, what I'm saying is this index, which is suppose 0 and this index is 9, I say add 32 to it. When I add 32, it seems that it is outside my range. So I'll say okay, come back. Now proceed with 2 to the power 4. Again 16 is outside. Start with 2 to the power 3. When I say 2 to the power 3, what will I do? I will take a hop from this position to 8 steps after this. So this is the index 8. And I'll say on reaching there, I will decide whether I should go behind or I should go in front, or I should return this particular index. This is the exact thing that I'll be doing. Now over here we have just stepped in at the correct position. So let us say it is not 9, it is suppose 8. We have to search for 8. Okay. So now we have stepped in, we have added 2 to the power 3, and we are seeing 9 over here. We know it is sorted, so what can we say? That our element, which is the target, will lie somewhere in this range, which is from 0 to 8 minus 1, that is 7. So basically this is going to be the range, right? We can say something like this. And from here, another thing, what can we say? See, this is a very novel kind of an approach, I guess, for many of you. So pay very strong attention to this. What we are doing, we first checked with 2 to the power 5. We said our target element lies before that. Simple reason is 2 to the power 5 takes us away, far away. Then we say try with 2 to the power 4. Again we went far away. Then we say 2 to the power 3. Again we said that yes, we are going beyond the requirement. Then we said okay, we will try with 2 to the power 2. But now the moment we say that 2 to the power 3 is not possible, we will limit our search to, we will say that after this we will limit our search to 0 to 2 to the power 3 minus 1. Make sense? This will become our search space. Next time we will say we will search with 2 to the power 2. So we will take a jump of 2 to the power 2 from here, and we will reach somewhere over here, and we will say that our target element is greater than this. Greater than this means it should lie after this. So this has the index 4. It means it lies, this tells me that it lies somewhere in 5 to 8. So what can we say from here directly? We can say that now again our search space has halved. We can see that now we have a search space of less than equal to 2 square. Over here you have how many? 2 square elements at max, and behind also you have 2 square elements at max. Makes sense? Okay. So now what we can do from here is, we can say now we are focusing on that. Our start value has become 5. Now what we will see is, or we can say that our start value is somewhere over here. The value that we have ignored, this is now our start value. This is 5. That is the index 4. I'm sorry. Yeah. Okay. So we are at the index 4, and what we are checking is that now this will be our start. So over here we say that our start has changed from 0 to 4. Now we will say from here, what is the step we can do? We can take a step of 2 to the power 1. Why not 2 to the power 2 once again? Because if we take a step of 2 to the power 2, then it will again step back into that part which we have already ignored. So we will take a step of 2 to the power 1 from here. That is over here. We will say that, yeah, the target element is greater than this. So we will say that, okay, so now this tells us that our range, this tells that our start now becomes, we have to search somewhere in the range, this is 6, this is 7, so in the range 7 to 7, maybe we can say 7 to 7 or 7 to 8, whatever is called, 7 to 8 suppose, and our start position, now it becomes position 6. Now what we are saying that, yeah, we can now take 2 to the power 0 step from 7. So 0 step from this index 7, where does it reach us? It tells us that, yeah, we are getting 8. So over here we are getting it. So every time what are you doing? You are doing basically this. Let me put it forth like this. So you have a start position like this. You are telling, I will first try to take the maximum power of 2 possible. Okay, I will start taking the maximum power of 2 possible. I will say, using this value, is my element located in this range or in this range? Now since I've taken the highest value of 2, definitely my next value of 2 does not exist in the array. So what can I say? Suppose this is 2 to the power x. So can I say that the next element will definitely be less than 2 to the power x plus 1, and from there what can we say? This is less than 2 to the power x plus 2 to the power x. So we know this is this is at a position of, this is at a distance of 2 to the power x. So from here we can say that this distance is less than 2 to the power x. Why? Because we have shown that this distance of this point, last point from the starting point, is less than 2 to the power x plus 1. We know 2 to the power x is the distance of this middle point. So we know that the rest of the distance is definitely going to be less than 2 to the power x. Makes sense? So I can't see the chat updating. If you are following it, then please or if you are facing any doubts, please go on intimating me if I need to go over any point. Okay, now what do we say from here? We say that this is going to break our array into what? Now our entire array, now the part of our search space is going to be either this part or this part. This part is less than or equal to 2 to the power x, and we know that this distance is 2 to the power x, so this is also less than or equal to 2 to the power x. So can I say that since I've got which part to survey now, my search space is reduced to 2 to the power x? Okay, now suppose we check that this element is greater. So we will say, okay, don't update this position. This is going to remain as the start. Now search the next index, which is 2 to the power x minus 1. You take certain index, and what will you see then? Once you take this kind of an index, you are going to observe, or you are going to check that with respect to this value, where should your target lie? Should your target lie over here or over here? And what can you say? Now, if I see that, okay, it tells me that it is smaller than the target, then I should shift it over here. Whatever you do, whatever is the observation, whether it lies in the right half or in the left half, the important thing over here is that both these parts are of size 2 to the power x minus 1 and 2 to the power x minus 1. So can we say our search space now decreased from 2 to the power x to 2 to the power x minus 1 using just one check, just going one step? And can we say in the similar manner that, okay, if we see that our element which we got at the mid position 2 to the power x minus 1, that is less than the target, then we should search only this range, and if it is greater than the target, then we should search this range. So suppose we say that this is the range we should target because our element, middle element, is less than the required value. So what can we say? We can directly take this start and we can move it over here. We can say this is now going to be my start position, and from here I'm going to do everything else, whatever operation I take. And now what will we say? That, okay, we can go to a maximum of 2 to the power x minus 1, this distance. After this we know everything is greater. I know this. So what will I say? Now I can take steps in terms of 2 to the power x minus 2. So I will again take a step of 2 to the power x minus 2 over here, and what will I say? I will ask the same thing, that are you greater or are you lesser than the target value. And in this manner, what will we say? The moment we actually break down these search spaces, we actually get something like this: 2 to the power x minus 2, then 2 to the power x minus 3, and dot 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 up to 1. At one point of time it will become 1. And what can we say? After how many steps will it become 1? We can say that after x steps, basically. So what is x? We can say then basically what is the total number. We know that 2 to the power x is the largest value, or 2 to the power x plus 1 is greater than equal to greater than n. We know this. That is why we have chosen 2 to the power x, because we know that 2 to the power x plus 1 is greater than n. From here we know that n is less than or yeah, log n is basically going to be less than x plus 1. And from here we also know that log n is going to be greater than equal to x, because we know that 2 to the power x is going to be less than equal to n. So from here we can understand that yeah, x steps, and that is going to be less than equal to log n. So from here we get x is less than equal to log n. So we can understand that here also, using this approach, we are able to find in log n time the the correct position of the value. Does it make sense? Do we need to see an example, or is it clear to you? What we are saying is greatest power of 2 possible, shift it over there. Then we are checking, okay, the next, the just smaller power of 2 from the start position, whichever you feel is a good start position, just check from there. You will check from there whether in which range it lies, and in this way you with granularity you decided. So basically, suppose your position from the start, your distance from the start is going to be something like this. Suppose it is 13. So what shall we say? Suppose there are 15 elements in the array. Okay, suppose there are 15 elements in the array, or suppose there are more 20 elements in the array. So what will I say? I will first try to do something like 2 to the power. Now this 13 distance, this is the distance, and 20 is the length of the array, or you can tell distance of the last element from the first element, whatever. Now what can we say? That 20 means how many bits are there in 20? It is 1 0 1 0 0. This is 20 in binary. So what can we say for 13? Will my fifth bit be set? This is the question I'll be asking. Will my fifth bit be set? So when I decide that no, my fifth bit is not going to be set. Why? Because if I add the fifth bit, I'm going to be adding 16. And if I go 16 places forward, the value that I get will be greater than my target value. So I have to come before. So I will say that no, the first bit is going to be 0. So we have something like this till now. We have 0, 0, 0, 0. Then we will say that now try with the second bit set to 1. If the second bit is set to 1, then we are targeting 8 steps after myself. If I go 8 steps after myself, A8 is going to be less than A15. Can we say? A13. We are searching for A13. So our target value is basically equal to A13. So we can say A8 is less than this. So what will we say? That okay, let it remain set and let us look for greater values. We will say since it is lesser, so let us look for greater values. We'll go to the next element and we will similarly call for it. That is the next element. Should the next element be set to 1? Suppose we set it to 1. Let us see what happens. When we set it to 1, now the sum becomes 16 plus 8, 24. 8 plus 4, 12. So we see A12, and we know A12 is also going to be less than 13. So we'll see, yeah, let it remain. We will see that a smaller value is there. Then we will say now try to add it. We will see that we on adding this 1, we will get A13, which is greater than, we will get A14. 1110 is A14, so we will get greater than A13. So we will say that no, since it is greater, you should not proceed over there, you should rather set it to 0. So we will set it to 0. And next we will try to add this. And we will say that, okay, now let us set it to 1. Have we got A13? Yeah, we have got A13, and this is going to match our target value. So in this manner, we can show that any number you can actually reach in log n steps using this. Make sense? Make sense? So this is just a different way of observing binary search, but a speciality is there. There is one speciality, and that speciality is that we are only shifting in powers of 2. We are only shifting in powers of 2. In powers of 2. Right? Which type problem we can use binary? I didn't get the exact question. What do you mean by we can use binary? I didn't get it. Binaries, binary lifting. We will look at that. But first of all, I hope this is clear. We are only shifting in powers of 2. Okay. So this tells us that from a certain position, from any index I, we can reach any index at any point of time. What is the maximum storage after which type problem we can use binary number? Whenever we require bit masking to tell us what possibilities we are looking for, maybe you are working on Hamiltonian paths and then you want to keep a track of what vertices you have visited. Those kind of situations we usually proceed to binary. So usually there is a separate set of problems under bit masking. So whenever you deal with bit masking problems, you require a good concept of binary number system. In other cases, for binary search, just for understanding it better, you need some concept of binary numbers. Otherwise, trivially also we can understand. So okay, hope that answers. Now from I, what are the different pointers we require? Do we need to, like, are we anytime saying that I plus mid we need to go to? I plus some any value? Are we saying that? No. We are saying that either we have to go to I plus 2 power 0, which is I plus 1, or we need to go to I plus 2 power 1, which is I plus 2, or we need to go to I plus 2 square, which is I plus 4, and so on. So how much of storage is required? Say I cannot directly proceed to any cell unless I store it. So can I say that if I have these values, then I can traverse and I can implement it successfully, this particular algorithm? I don't require start plus 1, start plus 2, start plus 3, everything. I require only start plus all powers of 2 possible, so that the destination is inside my array range. So if I contain all those powers of 2 possible, will that suffice for my for my answer? It shall suffice, right? So that is basically what the entire computation is all about. There you actually go. Now what can we say? That in case of a linked list, if you have this kind of a storage, that what is going to be, in case of a linked list, if you have this kind of a storage, that what is going to be 2 to the power 0 blocks after me, 2 to the power 1 block after me, and so on. Can we do binary search using that? If you have that kind of a pre-processing, can we do binary search using that? Suppose I have again 1, 2, 4, 7, 8, 18, 20, and I am searching for 18. So can I say now 1, 2, 4? Yeah, so I'll try 2 to the power 4. Can I say if I contain these pointers 2 to the power 0, 2 to the power 1, 2 to the power 2, and nothing else. From here also I contain these pointers. So how many pointers will each contain? Log n. Log of n to the base 2. This is the number of pointers I need to contain for every index. So for all the indices taken together, it is n into log n. Makes sense? So from here what can we say? That the moment I come to 2 to the power 2, I can say now from here I have the pointers to 2 to the power 2 to the power 0, 2 to the power 1. So I'll be trying 2 to the power 1 first. I'll be seeing it is lesser. So I'll be trying 2 to the power 0 from here, and I'll be reaching here. So in a linked list also, we can actually find out, we can apply binary search if we have this kind of a storage, n into log n. Okay, and we are applying binary search. Don't think we are just solving the problem of searching. We are applying binary search to solve the problem of searching. Otherwise, you could have done so many things, hash map and so many things. We are not using any other data structure. We are just using n log n links, and we are applying the same binary search which we could only apply on arrays till at the beginning of the session. So in these 30 minutes, we actually covered how we can do binary search in even a linked list. And this pre-processing you only need to do once. After this, whatever question I ask you, find 15, find 205, find 13, find 4. Whatever I ask you, you're going to find it for me. Make sense? So this is actually the idea. And this is the idea which we are going to very strongly use for LCA problems, for our concept of LCA and for binary lifting. So before that, tell me, is this idea clear how we are finding it? Now the thing is, how comfortably can we calculate it? How comfortably can we calculate all these, pointers? So let us check that. How comfortably we can calculate it. So suppose we have a linked list like this. Yeah. So I have something like 1, 3, 4, 6, 18, 21, 22, 30, 47, something like this. For this guy, what will I say? That the 2 to the power 0th next person, that is exactly the next person, there is nothing. So we can name it something like null. For 30, what can we say? Instead of null, you can also write 47. There are many conventions. You can choose any conventions. So after 47, there is nothing. So we can just choose 47. It depends on what you are doing basically. So anyway, so what can we say? For 30, we know the next one is 47. For 22, the next one is 30. For 21, the next one is 22. For 18, the next one is 21, and so on. Over here you have 18. Now the magical thing will start. So be prepared for this. You have 4, and over here you have 3. Now what shall we have? We will say that if we need the 2 to the power 1th ancestor of this guy, then dp of x I is basically equal to dp of x minus dp of x I minus 1 whole I minus 1. What does this state? This states that if I have to find 2 to the power ith ancestor, if I have to find my 2 to the power or 2 to the power ith next node, if I have to find 2 to the power ith next node, what will I do? I will search my 2 to the power I minus 1 at next node, and he will give me his 2 to the power I minus 1 at next node. So I will say, go to my next node and ask him his next node, and whatever you get, you are going to store that as your 2 to the power 1th node. This is the node which is located at 2 to the power 1 distance from it. Similarly, we will do this. If we have to go to a distance of 2 to the power 1, we will say go to a distance of 2 to the power 0, and for that guy, see what exists at a distance of 2 to the power 0. So using 30, I'll be going over here, and then I'll be fetching 47, and I'll be printing 47 over here. Make sense? We can directly copy it. Can we say that yes, this is located at a distance of 2 to the power I from here? This is located at a distance of 2 to the power 1 from here. This is located at 2 to the power 0 distance, and so on. Here also we have 2 to the power 0 and 2 to the power 1. I guess you all are following. Similarly, what can we say? We can copy these values. Similarly, we can say that yeah, for this also we first go to its 2 to the power 0th next guy, which is 22. We will go to its 2 to the power 0th next guy, which is 30, and we will copy this. And we'll copy in this manner everything. We'll have 22 and we will have 21 and so on. Now, over here, what shall we say? We have nulls and nulls over here. This one also will become null. Over here, when we have to use 2 to the power 2th ancestor, we will say go to 2 to the power 1th next node, 2 to the power 1th next node, and search is 2 to the power 1th next node. So over here, everything is null. So it will say, yeah, this is going to be null. 21 says go to my 2 to the power 1th next node. It goes to 2 to the power 1th next node, which is 30. It checks for its 2 to the power 1th next node, and it says that it is null. So from here, what do we get? that 2 to the power 2th next node is equal to 2 to the power 1th next node of 2 to the power 1th next node of this guy, which is going to be, for this 18, suppose for 18, what is the 2 to the power 1th next node of 18? That is going to be 22. So we will say 2 to the power 2th next node of 18 is going to be 2 to the power 1th next node of 2 to the power 1th next node of 18, which is 22. Watch this and understand what I actually wanted to do. This is precisely the formulation for it. So I said that when I have to jump in 4 steps, I will jump first in 2 steps, then in 2 steps. If I jump in 2 steps, I know where to reach. I know I have to reach 22. So I'll go to 22 and see that from there, if I take 2 steps, where I'll reach. I'll see 47. So I'll just copy it and I'll say 47. And then over here I can do the same thing. I'll jump to 21. 21 मुझे बताएगा कि 30 ले सकते हैं. So I will choose 30. And then all these we can calculate in a similar manner. This is exactly how binary lifting works. So I hope this idea is clear how we are storing it. So now we can understand that log n storage, log n times we can do the same thing. We'll just go on copying values and we can do the same thing. How are we transversing? I hope that is clear. We are moving to a particular location which is important to us, and we are copying some corresponding value within this list and getting the value over here. Making sense? So this is exactly the trick, and this is widely used in your binary lifting. So let us now quickly then go through our exercises. The first thing is how to find the LCA in a naive manner. What is LCA? First of all, LCA is something like this. You have got a rooted tree. You have got some kind of a rooted tree. So you have got a distinct parent to child relationship. Something like this. Okay, and you are asking what is the least common ancestor of this node and this node. So the full form of LCA is going to be least common ancestor. So what are ancestors? Everything that comes on top of this node is an ancestor of this guy, and whatever comes on the top of this node is an ancestor of this guy. We want the least common ancestor. So we can say this guy is a common ancestor of both of them. We can say this. And what can be the way of finding it? We can write down for all of them, we can write down the root to leaf paths. The root to leaf paths we can write down for both of them. We traverse from root to the leaf. So we can travel from root to leaf for both of them, and then what can we say? That last point where they are meeting, the last point where there is a common point between them, we can directly apply it. So we can directly have the paths with us, and then we can choose which is the last point where it is becoming equal. After this it will always be unequal. Until this everything will be equal if we look from the root to the end. So this is again a situation where we get monotonicity. We can directly apply binary search, but for this particular method we have to store the values, right? We have to store the values. That what is the root to leaf path of a particular node. We have to perform DFS, and then we have to store the values for all of them. There will be a huge storage, and that is the reason why it is not meant. Because suppose you have a list kind of a structure, so the total summation of the lengths, every node can be at a length of n. So a rooted tree may not be of log n height, it can be of any height. You can have up to order n height, you know that. So the length of the list can go up to n. So you can have up to n to the power, I think, like for all of them you can have up to n to the power n storage you may require. So that is a problem in this approach. Else we could have easily done it. But storing this n into n length is a problem. It will require a lot of time, and even the space will be insufficient. That is the reason we say we cannot apply binary search just by storing the root to leaf path. And what do? We say one thing, we can proceed from bottom to the top. Suppose somebody has told us that these are the two nodes we are going to observe. So first I'll say if they're at the same level, well and good. If they're not at the same level, then whichever is located below, something like this. Suppose I ask you, what is the lowest common ancestor of this node and this node? So what will I say? That first, whichever is located at a lower level, make it get to the higher level. Make it get to the higher level. Why it is so? Because a tree means definitely there cannot be multiple paths to this level. So in order to come to a certain level where they match, it needs to reach that certain level. What can that certain level be? That certain level, which will be the level of the least common ancestor, that will lie either above this level, which is the upper level among both these nodes, or on top of it. So our least common ancestor will lie somewhere over here. So we can say that, okay, we have to find for these two nodes, this node A and this node B, what can we say? That go to the ancestor, and when you see that you have come to the same level, suppose this is A dash, when you see you have come to the same level, now find out the LCA. You find out this is the common one, so you can say that yeah, for A and B also this is the least common ancestor. This is something we can directly apply. What can we say? That every time first you reach both the nodes to the same level, the lowest possible level, which will be the same for both, and then proceed one level upwards and see whether it is the same node or not. At some point of time it will be the same node, they will have the same parent. So you need to see whether next parent is the same. If it is the same, just print it, else proceed 2 steps and so on. So over here you can see that everything is fine, but I am requiring to travel so many steps above, and this can again take order n steps. Hence we can say that once they come to the same level, why don't we apply the binary search? We know that now they are at the same level. Now both the nodes are at the same level. So we know that after some steps this will be reaching the root. This is the root, and taking the same number of steps this is going to reach the root. Why? Because the levels are same, and this is a tree, a rooted tree. Because of rooted tree you will find that the levels are the same, so in the same amount of time they'll be reaching the root. So what can we say? That at a particular point of time, maybe we can say that somewhere over here we will see that they will have the same parent, and after that they will move together. So we need to basically find this point, and this height can go up to order n, but we need to find in a shorter amount of time. So can you relate it that it is similar to your linked list kind of the question, where you say we are going to take the same kind of steps, we know it is located at the same distance, and what shall we say? That first take one step, or first take a giant step, and decide that taking that giant step, is your intersection point above this or below this? If you see that you have not yet intersected, these two nodes are still disjoint, then we will say that it is above this. So this is basically the point, and we will say that now choose this as a starting point. If you had A and B over here, now choose A and B over here, and from here you continue the search for the least common ancestor. Suppose you end up somewhere over here. What can we say? If it goes somewhere over here, it says that okay, next 2 ka power it will apply, and it will reach somewhere over here. It will say now search downwards. You cannot get over here, so cancel this entire path. Okay, so what this is telling is this is going to be common, but you can get a better common. You have got this common, so you will say that okay, answer first of all gets updated to this X node. So it first of all says that this can be an answer, but now you don't need to search anything above this. You have already found something, so now search below this if you get even a least common ancestor, even something below it. So it will search in this particular part, so it will apply some 2 to the power lesser power, and it will eventually get to the actual point. Make sense? So what do we know? Since we have got them at the same level, we know that now there exists a certain distance which is C from the point of intersection, and we know that suppose we call this as okay, so we can say now if we reach the parents, the parent or the ancestor of A, the ith ancestor of A will be equal to the ith ancestor of B for all I greater than equal to C. Makes sense? C is the distance of this intersection point from these two nodes. We have brought them to the same level. If one was at a smaller level, we have brought it to the same level. Now we can say it is going to hold, and this is the monotonicity. And we can say less than C, this is not equal parent of basically ith parent. This is not equal to the ith parent for all I less than C. We can say something like this. And when we know this, what can we say? We are getting a monotonicity. So let's apply binary search and get our things done. How are we going? How are we traveling to this point? Again, using the same kind of things. We know for every node what lies at 2 to the power 0 distance, what lies at 2 to the power 1 distance, what lies at 2 to the power 2 distance, and so on. We know all these things and we are calculating in the similar manner. For 2 to the power 0, we are calculating first for all of the nodes. We are saying that for 2 to the power 0, whoever is the parent, he will be parent of x 2 to the power 0. Then we will say that if this is y, we will say parent of x 2 to the power 1 is going to be parent of y 2 to the power 0. Makes sense? So this is how we proceed. So in this way, once we do like this, our entire solution is going to come. Our entire solution in the sense that we will have all the ancestors for all the nodes. I'm sorry. Yeah. Makes sense? We'll have the ancestors of all the nodes. So after this, there is just a small task. All that we need to do is, now while applying the LCA, for every node, first we have to get to the same level. So in order to get to the same level, you can say we need to take a jump which is equal to level B minus level A. Suppose A is over here. We need to take a jump which is level B minus level or level A minus level B, whatever that difference. We can say that using a similar paradigm, if you have to take a jump of suppose 13, we know how to take the jump. So first of all, 13, we can say 13 comes in these steps. In the steps of 8 plus 4 plus 1. So we can first take a jump of 2 to the power 3, then a jump of 2 to the power 2, then a jump of 2 to the power 0. And thus we'll be reaching the point which lies at the same level as B. Then we need to check if this itself is the answer, if A itself, whatever it is, if it itself is B, if they are the same thing. If they are the same thing, then we are done. Otherwise, we will say now do binary search. The same kind of binary search. We'll do this. So first we applied the kth ancestor. We know that the level difference can be LB minus LA or something like that. LA minus LB, the modulus value. We will first take those many steps. By how? Again by our binary search method. We will take first the highest power of 2 which exists in this value. If this is 13, we will first take a step of 8. From there we will take a step of 4, and from there we will take a step of 1. In this way we are going to reach this particular node in this particular level. Then we are going to say now from both the nodes we will try to reach the common one. So what is the method we can apply? Binary search. So the least common one we can apply by binary search, and we can find that out. How we are applying? Using n log n storage. So this process uses n log of n to the base 2 storage. Okay, any questions? So this session, actually I had taken this session in a different way much before, and over there it took me much more time, probably because there were a lot of questions, but today we did not have any questions. But anyway, if you have any questions now, you can ask. If you have any questions or any doubts or any queries now relating to this question or the applications of this concept, then you can ask me. So see, using this simple approach, you can do such a lot of things. And the basic approach was such a simple thing that you go in steps of 2, in powers of 2. When you go in powers of 2, it becomes so magical. You can say that now you don't require indexes for all the positions. You just require n log n, pointers. Not so many pointers. From everywhere, you don't need a pointer to every other place. Without that, you can manage. And what you are allowing, tree and your basically linked list, these are all non-index structures. They don't have indexes. And basically you are enabling all of those non-index structures to perform binary search upon them. So it's definitely a magical method, you can say. Okay, so that's about the storage. Now, are we left with anything? So what is the total time complexity? Let us analyze that. The total time complexity, if you consider, you have suppose n nodes. You want to do q queries where every query will give you some AB and you have to find the LCA of A and B. What you can do is you can first form the structures of the ancestors of those nodes, and over here, first of all, in linked list I was drawing from right to the left. I was marking everything from right to the left. Is that important? You might think you'll be able to find out we can also do that from left to the right, right? So yeah, we can also go from left to the right. What is the reason? Because of this particular relation. See, in this relation we are saying that this I minus 1 is only needed. We are saying only these I minus 1 values are needed. So if for all, like suppose I equals to 2, I calculate everything successfully. Then for I equals to 3, what can I say? For all the values dpx2, this is going to be stored. dpx2 for all x, it is going to be stored. And whatever you are going to find the value over here, you can say again I minus 1 is going to be 2. So again it is going to be stored. So from here we can understand if you calculate for a particular I all the values, and when we then look for the next value of I, all our required values have been pre-computed. So it becomes pretty easy. Over here you could have also started from here. You could have said we are first forming this and then we are forming what? Then our 2 to the power 0th next elements, 2 to the power 0th next, which is 4. This is going to be 2 to the power 1th. And then we can form for all of these. It will reach over here. It will reach to 4 and its element it is going to copy over there. It is going to reach 6 and 6th next element, which is 18. Then we can say over here similarly we have all these values. Now suppose we are doing from here, we can say yeah, from 4, due to this 4 go to this 4, and from here take this 18 and place it over here. So we know that at a distance of 4 now 18 exists. We know this. So that's it. This is how this becomes possible. When I know 2 to the power 1th distance value for all of them, 2 to the power 2th distance value is not a big deal. I can just go to the correct node and I can go on transition till I get the value. Make sense? Well. So the time complexity comes out to be for n nodes, for all of them, what I am worrying about. Just the log n next nodes or the log n ancestors. So we can say this will lead to n log n computation. Why these many values I need to compute? And for computation of every value, I need to do just one step, which is go to the already computed value, go to this already computed value, and then look at that particular node and look at its own already computed value. Both are already computed. I just have to use order 1 operation to find it out. If for all the x I minus 1 is stored, it's very easy to do the rest of the step. Right? So over here we can say we can do in order n log n. What next? Now I can say for all the queries, what can we say? That first we can find the kth ancestor in how much time? In order log n time. So whichever is at a lower level, suppose A is over here, B is over here. So we first of all need to reach to the same level, and then we will say now search from here. So both are login operations. This is also login, and after this we know this is standard binary search. This is also login. So we'll be applying login over here as well. So we'll have for all queries taken together, we'll have q login total time. So our total time complexity comes out to order n plus q login. Over here, okay, if it is big O notation, we don't use logarithmic basis, but in our case, it is the base of the logarithm is 2. We can also try for using using k instead of 2. We can say that every time we are going to jump in k to the power 1, k to the power 2, what will that decrease and what will that increase? This was actually a very interesting discussion I had the previous time when I taught this topic. So from here you can get that due to the choice of 2, my total storage is actually something like this: n log of e log of n to the base e divided by log of 2 to the base e. So if we increase the value of k, if we say that we are going to choose higher k, we are going to jump in 3 to the power 0, 3 to the power 1, 3 to the power 2 and so on, then this denominator is going to increase and hence our storage is going to get optimized. Our storage is going to get optimized, but we will have to pay the price in our time complexity analysis. Over there, you will see that we need to take many more steps. So the constant is going to rise over there. So over there, if you say that, okay, for this value, I have checked that if I go k steps, then this is greater. Then I have to check with k to the power 0, that is 1. K to the power 0 and again k to the power 0 and so on. I need to proceed in this manner. So what can we say? It is this extra k minus 1 computation has to be followed. Extra k minus 1 computation. And we can say this will eventually lead to log of n to the base k. And if you look at this, this is basically n into log of two to the base. Okay, let us forget this. We don't have this. Log of 2 to the base k and log of 2 to the base n. 1 by this multiplied by this multiplied by k minus 1. So you can see this is the factor which is greater. So we had log of n to the base 2, and over here you are finding k minus 1 divided by log of k to the base 2 multiplied by log 2. And this is a very fast analysis just to show that if we increase the value of k, this is going to favor us. This is going to reduce it, but this part is even more. This is going to increase it. So in some cases we'll have to, more time will be consumed. So that is the reason we choose k equals to 2. So that, we choose k equals to 2. When we choose everything in, that is every jump in powers of 2, it actually turns out to be quite good, good enough for our purposes. That's it. But yeah, you can analyze it. So that's about LCA and binary lifting. Any questions in the next 1-2 minutes you can ask. We can close at 8. Do you want to see the code? Do you want to see the code for LCA? Okay, if not, then we are done. Maybe I can take 1 or 2 questions and then we can close. So do practice this, do observe it, do mention in comments or anywhere if you want to study anything else, any other kind of topic you want us to cover, related topics. And if you have any doubts, you can always mention. We don't stay active on all these things. I don't visit the links after I perform in the videos. So maybe I'll be informed by the team or by somebody that there is a question, and we'll take care of it. Okay. Okay, last but not least, yeah, I was forgetting this. So we have, these are the batches which are offered at, yeah, these are the batches which are currently offered at Unacademy. We should cover this. Just a second. I'll be in this display. Okay. So okay, let's continue with this one only for the time being. Recents, copy. Yeah. So these are the batches which are currently being offered at Unacademy. You have Mahayodha batch. I'm covering this batch currently. It's a 2-month master course in advanced programming topics. Eklavya 2.0, this is for beginners, and this takes the beginners from beginner to advanced level in a course of 8 months. And then you have Brahmastra 2.0, which is explicitly for college and off-campus placements. All of these batches start on 6th of July 2021. So you get a structured learning path, one subscription and unlimited access to all batches or courses, successfully contest in competitions like ICPC and CodeJam, best coders of India as educators. Subscription fee is nominal. This is the batch structure, Mahayodha. So you can see it starts with the advanced mathematical topics, then proceeds to advanced dynamic programming, segment trees, advanced concepts of graph theory, mixed problem solving. Then you have Eklavya 2.0, and you have this beginning programming fundamentals, then the intermediate topics, then the advanced topics in Eklavya, which is going to be offered in Java, or which is being offered in Java. Then you have Brahmastra 2.0, which is explicitly for college and off-campus placements. Coding will happen in C++ here. So you'll have this beginner and intermediate topics first, and then you have some relevant advanced topics which are asked in interviews. You'll have interview problems in the last 2 weeks. Okay, these are your educators. You have ICPC World Finalists, you have Code Forces Grandmasters, and alumni of top companies. So we have been a recent addition to the team. Personally, I am a 6-star rated coder at Code Chef, and I have been a master at Code Forces, and I've been to the ACM ICPC Regionals 2019, and yeah, I'm going to join Google quite soon. So that's about myself. You will get live interactive classes, you will have practice relevant problems, you will have TA doubt support, and these are educators. You can look at their profiles, and this is basically how the pricing looks like. As you proceed to the higher durations, you get greater discounts. On top of everything that you get over here, you can fill an extra 10% off on top of all these if you use my referral code Saptarshi 172. Okay. Cool. Any questions? Okay then, take care, solve problems, keep coding, and good luck with all your endeavor. Get yourselves vaccinated. And that's it. Have a nice evening. Bye.